All right, this is part 2 of nuclear chemistry. And right at the end of part 1, I was talking about the valley of stability. And I forgot to mention that the reason why the N over P ratio increases with atomic number has to do with these repulsions between the protons in the nucleus. And as the isotope has more and more protons in it, with a higher atomic number, there's that repulsion that gets quite large. And so the more neutrons that are present kind of dilutes the proton-proton interaction and stabilizes it. So the more neutrons are needed to stabilize it. All right, anyway, this is the part 2 here. We're going to first look at the kinetics of nuclear decay. All nuclear decay is first order, so that's good. And you remember probably from kinetics, and we had from kinetics the natural log of A over A initial for first order decay is negative KT. And you can see here that it's similar, except that you have N instead of A. A little bit different symbolism here, but it means something different. Here, this brackets mean concentration in moles per liter, but here N is the number of counts. So you have a radioactive Geiger counter or a scintillation counter that's counting the number of nuclear decays per unit time. So you have your initial counts, and then sometime later you have your counts at time t. So that's the only difference. First thing, we go from natural log to base 10 log, so there's the 2.303. Then you use K is 0.693 over T1/2, plug it in here. And then the final expression is the log of the ratio of the counts, and then that's equal to negative 0.693 times T divided by 2.303 T1/2. This is just the form of the equation that's used usually by nuclear chemists, excuse me, and it's good because you can just substitute the half-life in there, and the half-life of every isotope that undergoes nuclear decay is known. You can find those in tables easily. All right, so we'll go quickly through a calculation where P32 is the radioactive isotope. It's got a half-life of 14.3 days. And so if the phosphorus-containing compound is used 5.5 days after it was prepared, what fraction of the radioactive isotope originally present still remains? Okay, so you have the half-life here, T1/2, then you have T, and the fraction is going to be equal to NT divided by N0. So we can use our equation, which is base 10 logarithm NT over N initial negative 0.693 T over 2.303 T1/2. So for us, it's logarithm of the ratio, which you're going to solve for, negative 0.693 times 5.5 days divided by 2.303 times 14.3 days. And of course, you do not have to go to seconds. Just keep them in days because you can see how the days are going to cancel here. The day unit is going to cancel. So then you have logarithm NT over N initial, and this is equal to negative 0.116. Then you solve for the fraction NT over N initial, 10 to the minus 0.116, which is equal to 0.77. So you get the ratio NT over N0 is 0.77, and that means 77% of the counts still remain, or of the radioactive isotopes still remains. It's not the amounts decayed away, it's the amount that remains. Okay, so then part B, suppose the sample weighs 0.28 grams. How many grams will remain after? So we just calculated the fraction for 5.5 days. So how many grams will remain after 5.5 days? So that one's pretty straightforward. You have 0.28 grams. And if you take 77% of that, 0.77, this will be equal to 0.21 grams. So the answer is, after 5.5 days, 0.21 grams of the original 0.28 grams still remains. Okay, it's pretty straightforward there. We'll go ahead to the next slide. Now, this one's got a lot of detail here. Sorry about that. Get a little carried away. All right, so radioactive dating technique, that's you can learn how old a substance is if it had ever been alive. So a piece of wood, for example, came from a tree. So we want to know how old the wood is, for example. So we use the idea that carbon-14 is present, as well as carbon-12 in living systems. So let me just read it here. So carbon-14 decays by beta emission with a half-life of 5,730 years. Wood and carbon containing fossils from several thousand to 50,000 years can be dated, and that's because it goes through several half-lives there. But not too many, so it's right in that little window there. So they can be dated, wood and carbon can be dated by looking at the number of carbon-14 nuclei that are present. So carbon-14 is produced in the upper atmosphere right here. And it says here, by interaction with cosmic rays, those are going to be gamma rays and high-energy particles like neutrons. So by collision, then you have this nuclear reaction that takes place where nitrogen turns into carbon-14, proton given off here. So carbon-14 decays back to form the nitrogen again, but this time it's by beta emission. And the rate constant for these two reactions are different. If the first reaction occurs more quickly, then there'll be a quick buildup of carbon-14, and then it's a little bit slower to decay. So that means that some of it will, remain. In other words, it builds up, but it decays more slowly. So at any point in time, there'll be this ratio of carbon-14 to carbon-12 concentrations just based on those differing rate constants. So in the upper atmosphere, there's going to be this constant number, this constant value associated with this concentration ratio here. It's also true in the lower atmosphere, but now the carbons have been incorporated with oxygen to form CO2. So, but the amount of 14 to 12 is the same. CO2 is taken up by plants, so the carbon within the plants has the same 14 to 12 ratio. Animals feed on the plants, so the carbon within animals has the same ratio. And then when they die, the animal or the plant dies, the carbon-12 stays the same, but the carbon-14 decays away. So the ratio of those abundances, isotope abundances or concentration, changes in time, and then the ratio becomes a clock. So the longer it goes, the less carbon-14 there is. All right, so let's look at this example. It's kind of interesting. This one is a piece of charcoal from a tree killed by a volcanic eruption that formed in the crater in Crater Lake. Crater Lake is a lake in Oregon. It's just just north of the California-Oregon border. And I've actually been there. You can drive up this mountain, and at the top of the mountain is this lake where when the volcano blew up or erupted, it actually blew off part of this mountain. So it's a beautiful place to go. It's a state park. National park, probably. Anyway, so here's the charcoal, very old when the tree died, from when the tree died. And you have the counts here, the units are a little bit strange, but so I put them in bold. So 7 disintegrations of carbon-14 nuclei per minute per gram of total carbon. All right, in living matter, it's 15.3. So you've got your ratio here, 7 to 15.3. You want to determine the date of the volcanic eruption. Excuse me. Okay, we can write that out. All right, so we have base 10 logarithm nt over n initial negative 0.693t divided by 2.303 times the half-life. And this time you have your ratio 7.0 divided by 15.3 negative 0.693. And let's see, we're looking for the time. We know the half-life, which is 5,730 years. Do we have to go to minutes and seconds and days and all that? No, we just solve for years here. Keeps it simple. Okay. And let's see, if you solve for time, it ends up being 6.5 times 10 to the third years ago. And then you can calculate what that is BC. So this is 4,520 years BC. Okay, so either way is fine. Certainly you can just write it that way and know how many years ago it was. Okay, so now we move on to discussion about fusion and fission. And we'll start with fusion here, a nuclear reaction in which light nuclei combine to give a more stable, heavier nucleus, plus several neutrons, and energy is released. So here you have light nuclei. This is deuterium. Let me make a note here that, and I think I've given you this before. So the hydrogen isotopes 1, 2, and 3. The first one is hydrogen. The second one is deuterium. And the third one is tritium. And hydrogen, by difference here, has 0 neutrons. Deuterium has 1 neutron, and tritium has 2 neutrons. Okay, so you get these nuclear isotopes. And this one is deuterium, this one's tritium. So when they combine, you get a helium nucleus plus a neutron plus some energy. In this case, you have 2 deuteriums combining to form helium-3, neutron plus energy. So for fusion, the nuclear reaction is very slow because it has a very high activation energy. And one must heat to 100 million degrees for this reaction to start. Use of lasers and mirrors have achieved this in the lab. It's not practical to build a fusion reactor at this time. But during World War II, the hydrogen bomb was a fusion reaction, energy from that, and so in that case it was a fission reaction that triggered the fusion reaction. So high energy here to trigger the fusion reaction. All right, anyway, the fission is a different process. Here you have a heavy nucleus that decays to form 2 lighter nuclei, and neutrons are given off, and there's nuclear energy as well. So californium decays by neutron decay, and quite a bit of energy associated with that, as you know. So before we're going to do calculations for nuclear energy for both fission and fusion, but before that, let's look at this thing called binding energy, the nuclear binding energy. So first of all, a nucleon, you see that term very often in nuclear chemistry discussions, and it's either a neutron or a proton. So it's just kind of the generic term for the nuclear particles. So when nucleons form a nucleus, right, so when the protons and the neutrons come together to make a nucleus, there's a mass decrease. And you have the mass turning into energy, E equals mc squared. So energy is released as the system becomes more stable, and we're going to calculate that energy. But first of all, just general knowledge, if you have a proton and a neutron coming together to form a nuclear particle, in this case it's an isotope, if you combine the electrons as well, then you can have an atom or an isotope. And then energy. So in other words, I'm giving it to you in reverse here. So 2 protons plus 2 neutrons plus 2 electrons was helium plus some energy. So energy is given off because of this conversion of mass to energy. But we look at the reverse process here to talk about how tightly bound the protons and neutrons are in the nucleus of the helium. So how much energy is needed to break this up into protons, neutrons, and electrons? And I don't include the electrons here because their mass is about 1,800 times lighter than the protons and the neutrons. So in terms of sig figs, it's really not important to add them. All right, so the binding energy is how much energy it takes to separate these, and that's an indication of how strongly held they are. All right, now this is a very well-known binding energy curve graph, and so there's a lot of information here. The outcome of it is to show that very light particles here have a very small binding energy, like hydrogen, deuterium, tritium, helium-3, even lithium-6, like that. So on this left-hand side of this curve, fusion occurs or can occur. And it goes all the way up to iron 56, which is very stable. So the binding energy is going to be very high in this region. But let's go ahead and read this paragraph. So for fusion, there is a strong nuclear force that allows the protons and neutrons to combine to make the nucleus. So there's 2 forces. One is the nuclear force, the other one is the Coulombic force. But for the nuclear force, the light nuclei have the best chance of this happening. As the number of nucleons increases in the nucleus, there's an increasingly repulsive Coulombic force. And that's what I referred to at the beginning of this video. So this Coulombic repulsive force that occurs between the protons. So proton-proton repulsive interaction. So thus a high Coulombic activation energy must be overcome to form the nucleus. And remember, you have to heat it to 100 million degrees, that kind of activation energy. So when the number of nucleons gets higher, it gets more and more difficult to fuse 2 isotopes. Okay, so if you look at some of these binding energy curves online, you see that there's a line drawn right here, and they go, okay, to the left of that, fusion can occur. To the right of that, it cannot occur. But what we find instead is that these heavy nuclei way over here, they're not going to undergo fusion, but they can undergo fission. So usually they're labeled here that they can undergo fission. But the point of this graph is to show what isotopes can undergo fusion, and the answer is the light ones that have the least number of proton-proton interactions in the nucleus. Okay, so now let's go ahead and calculate the energy that's given off. So this is, I put the electrons in here this time. So 2 protons plus 2 neutrons plus 2 electrons to make helium-4 plus energy. So this energy is the negative of the binding energy. Okay, all right. So now we have, it's going to be products minus reactants. First you have to calculate the masses of each of those. We're going to leave out the electrons here. 2 times the mass of the proton plus 2 times the mass of the neutron gives you 4.03190 plus the mass of the electrons, but that's not going to be huge, as I said. All right, but the issue here is when you look at the molar mass for helium, it's 4.00150. We get this from the periodic table, and that is not equal to the sum of the masses of the individual particles. What happened? So when the helium's formed, some of that mass is lost and the mass converts to energy using E equals mc squared, Einstein's equation. So you take the molar mass of the compound, which is less than the sum of the molar masses of the particles. That difference is negative, so there's been a mass loss or a mass defect, and then put that over here, and you can calculate times speed of light squared. You can calculate the energy. But the point here is that mass turns into energy during the nuclear reaction. Okay, so now we got more detail here. This is the calculation for the energy of nuclear fusion. And this example is deuterium plus helium-3 forming helium-4 plus a proton plus energy. So you have 2 light particles coming together to form a heavier particle, heavier nucleus, and then a proton is given off plus energy. So sum of the mass from here ends up as energy. So you're going to calculate the mass defect. The sum of the masses here minus, well, here I should say, minus the sum of the masses here. You'd be given this in a problem if I were going to ask you this. So you're going to take the mass of helium-4 plus the mass of the proton, and then you're going to subtract the mass of the deuterium plus the mass of the helium-3. So when you do that, you get, and this is a unit issue, so watch for this. When you subtract, you get AMU per particle, right, per atom or per isotope. But if you remember from last semester, you can substitute AMU per molecule or AMU per atom or isotope, whatever. You can substitute units grams per mole for AMU. So once you do that, then you've got basically a molar mass unit here, grams per mole. But we're going to calculate joules, and a joule is a kilogram meter squared per second squared. So our grams have to go to kilograms here to prepare for that calculation. So this is 10 to the minus 2 here. You divide by 1,000, you're going to get 10 to the minus 5 kilograms per mole. And then go ahead and calculate the energy. So it's this mass defect here times speed of light, 2.99, 10 to the 8 meters per second squared. And it'd be ideal if we had a few more sig figs here, but I didn't know them off the top of my head. All right, you put that together and you got a kilogram meter squared per second squared. So that's a joule, and then it would be per mole. All right, and then for 1 atom, delta E, you're going to take per mole and make it per atom. So you just divide by Avogadro's number. So you have 10 to the minus 12 joules. Now ask the question, is that a lot of energy associated with an atom or two? That is a huge amount of energy. All right, but nuclear scientists use this mega electron volt unit instead of joules per atom. So there's just a simple conversion factor that 1.602 times 10 to the minus 13 joules equals 1 mega electron volt. You'd be given that conversion on a test. So then put that together and it's negative 18.36. And I really should only have 3 sig figs here because I only got 3 here. So this should be negative 18.3 mega electron volts. All right, that is an enormous amount of energy associated with one atom. It's really huge. So, okay, now this is an interesting representation of nuclear fission. I just took this from the internet and I haven't labeled it. I should credit it as well. But a lot of my figures here I pull from the internet and they're free, but I need to reference them. In any event, let's see. So this is fission, and let's blow it up a little bit. In this example, you have uranium-236 here, decaying to form barium and krypton. So that is a nuclear fission reaction. These little circles here are neutrons, and you hit this uranium with neutrons. So it's kind of a high energy collision. You shoot the uranium with high energy neutrons. And when it absorbs the neutrons, then it decays away to form the two nuclear products, fission products. And in addition to the barium and the krypton that's formed, you get 3 neutrons back. This is the basis for the chain reaction, where you start with 1 neutron, then you get 3 neutrons. Okay, each neutron will react with another uranium-236, and there should be a third one in here as well. And then this time, different energies. You can get this reaction, the first reaction here again, but there are other reactions that uranium undergoes. One is to form cesium and rubidium with another neutron coming out, or to form strontium and xenon with 2 neutrons coming out. So that there's actually 3 reactions so far we're looking at here. And it's a good representation. It's not, I mean, it really should be a third one here where this just kind of reproduces itself. But in any event, the neutrons are here. They're reacting with more uranium. In this case, now you're getting xenon and strontium. Here, another neutron reacts with the U-236. You get 1, 2, 3 neutrons plus barium and krypton. That's this one right here. Over here, this 1 neutron breaks up uranium. You get rubidium and cesium. So that's this reaction. And then this one, I don't think we saw that one before, but 1 neutron again can make ytterbium and iodine. So more and more neutrons. There is heat given off for every single one of these nuclear reactions. The heat is raising the temperature of the system. When these heavy nuclei are first formed, they're in the gas phase. And so you have this expansion of the gas and tremendous energy, tremendous expansion. And if this thing just keeps going and going and going, where more and more neutrons are being produced and then reacted with uranium, it'll just blow up. Okay, so that's the basis of the nuclear explosion. Or you can use it either as fuel, it's for useful purposes, or you can use it for war purposes, bombs, and so on. But there's also, if you can capture the nuclear energy from fission or fusion and use it for heating and other electrical applications, then it's worth it. Okay. All right, so I'll comment on that again in a minute. But first, let's calculate the energy of a fission reaction. And it's pretty similar to that for the fusion one. In this case, you have a neutron that reacts on the slide before it was uranium-236, but U-235 has 3 reactions. I'm just giving you one of them here. So it's very similar with neutrons being given off. And this is the one that comes from the purification of naturally occurring uranium. So naturally occurring uranium contains, for the most part, U-238. And then a very small part of 235. There's 236 as well, but during the purification process, which is kind of complicated, that was a method that was developed during World War II, and it was possible after many purification steps to get a significant amount of U-235. So when uranium is mined, it has yellow color. Actually, not yellow. I think it's gray when it first comes out. It's reacted with oxygen to form uranium oxide compounds. Those are yellow. And that, you've probably seen pictures of that in the news. It's referred to as yellow cake. So you have uranium with the various isotopes bonded with oxygen to have yellow cake. And then that is sold to people who want to purify it. And in the news, sometimes you see those pictures of the scientists around those great big centrifuges. And so you can, just by mass differences, you can separate out U-235 from U-238. And so it's a complicated, long, painstaking process. And so when the question comes up, is this country nuclear or not? You know, when are they going to become nuclear? Well, it's all about purifying naturally occurring uranium to get out the U-235. So what is the time frame for that? That's usually what they're referring to. All right, so for this one, you have a neutron reacting with 235. You get xenon and strontium, 4 neutrons plus some nuclear energy. Same thing here. You've got a list of the nuclear particles. You're going to take products minus reactants. So the mass of xenon, the mass of strontium, 4 times the mass of the neutrons. And I think I'm missing a parenthesis here. Yeah, I need another parenthesis here. And then you're subtracting the masses of your nuclear starting reactants. So this is the mass of the neutron, and this is the mass of the 235. All right. Then that is negative 0.18464 AMU. Quickly, you just rewrite it, and you put grams per mole. Then you divide by 1,000, put it in scientific notation, you get kilograms per mole. Then you're going to use this delta M here in the E equals MC squared equation. So here it is again. And then you're going to multiply it times the speed of light squared to end up with some energy here. This is 10 to the 13 joules for 1 mole. That is a tremendous amount of energy. So, but as I said before, the nuclear scientists like it in terms of per atom. So first thing you're going to do is divide by Avogadro's number. You're going to take that number over here and then convert to a mega electron volts again. And this is 171. You put the negative sign just to indicate the energy is given off. So 171 mega electron volts per atom is pretty big. That's a large amount of energy converted there. So next is the idea that the nuclear reaction, the fission reaction, can get out of control and it can explode, right? So first is this concept of the critical mass. If you have less U-235 material than 55 kilograms of it, then it's below the critical mass, and it could be sustainable, and it's possible if you don't have enough that you can just, if you're not greater than 56 kilograms, then you could use that energy for a peaceful purpose like the ones in the figure below, where you can get electricity from it. So, but if it goes over, if you have more than 55 kilograms, it's possible then for it to get out of control. So below, the energy gets dissipated, but above, there's just too much energy in the system, and so it can explode if it's over 55. So how can one control this runaway situation if you're over 55 kilograms? And so if it's not controlled, it can become a bomb. If it's controlled, it can be used as fuel. One must use a neutron absorber like cadmium or boron. I think hafnium as well is a good one. That can be used to absorb the excess neutrons. So they're good neutron absorbers. And if the neutrons are being absorbed, then they're not causing this chain reaction to continue. So these are two diagrams associated with nuclear power plant. Whoops. And this first one, I love this diagram. This is the chamber, whoops, on the right here. And you have these cylinders that you can slip these control rods down into. It's actually on the left-hand side, you can see it better. So let's see, I guess the silver here, these are going to be the fuel rods. So this is just the nuclear material shaped into these rods. And then you intersperse them with these cylinders, and then you can slide these control materials like boron into the orange cylinders. So when the control rod is in close contact with the nuclear material, the fuel rod, then it can quench that reaction by absorbing the neutrons. And so if you want to control it, you move this part right here, you move it down. If you want to have more reaction, more energy, then you pull it up. So it's about this part, moving it up and down. You move it down to control it, and then you move it up in order to accelerate the reaction and get the energy from it. Okay, so then the other part here is the nuclear power plant basics. So you've got your fuel and your control rods that you can move them up and down. And let's see, you have the heat coming from the reaction is going to boil some water in this region, and the boiling water, the steam associated with that comes up into this part right here, and as it's moving this turbine around, moving it around. So as it circles, it's circling this part, which goes off to generate electricity. You always have this interesting effect where, you know, when anything's magnetic and turning, it generates electricity. So that's kind of the basis of this. So then the water comes back, and it has to go through this cooling tower, and cooling towers can be seen from the street. They're quite large. And so the steam has come through here, turn this mechanism here to generate electricity. Then the steam gets condensed. Once it goes through the cooling tower, and lots of times seawater is used for this. In California, on the way to San Diego, there's an old power plant that had that. And it was just sitting right at the beach because the cold beach water was the cooling material. And anyway, once it condenses, then the cold water comes back and it starts all over again. All right, quite a bit of energy associated with that. And here is our last slide. Just to put things into perspective here. So if you had 1 gram of U-235, it releases enough energy to raise the temperature of about 66 million gallons from 25 degrees C to 100 degrees C. So you've got you're going to boil, right? You're going to boil 66 million gallons of water with 1 gram, the energy from 1 gram of U-235 fission. By comparison, 1.65 million grams of octane or fossil fuel must be burned in order to release the same amount of energy. So it is incredible, the idea that you could use nuclear energy to, power the energy we need in our homes and our businesses, everything. The idea that we could do that is absolutely fantastic. The problem, of course, is with fission, the products of the nuclear reaction, like barium and radium and thorium and some of the other ones we saw, they are radioactive themselves. And so you have this waste, this nuclear waste that's being produced, and how are you going to get rid of that? It's radioactive. So in the early days, it was just buried, encased in lead and then buried off some remote area. Nowadays, the nuclear fuel is used all over again. So it's recycled at least one time, if not more. So the waste is a lot less than it used to be. But still, sometimes when these nuclear waste materials are buried, they're encased in lead, but then they start leaking out. And up in, Utah, I think they've had some issues with that. Plus, in California, the issue of having a nuclear power plant on a earthquake fault line. We kind of dumb. We actually did that up near San Luis Obispo. They had to shut that one down. So, there's issues associated with it, and Americans aren't too keen on the idea of using fission for our energy. But, excuse me, in France, forgot the number now, somewhere around, I don't know, between 70% and 90% of all the energy to power the country, the entire country, is fission. So they've had great success with it. Of course, you have the possibility of terrorism as well. So anyway, that's for young people like you guys to think about and figure out better ways to move forward in the future. All right, that's the end of our course. Hope you enjoyed it.